Hi, so my name is Mohamed Kassem. I am the co-founder and CTO of Efabless, and I'm going to talk to you today about, creating a world where a 14-year-old designs a chip. So I wanted to start first by saying, why is it hard to design chips? It's in general limited access to knowledge, technology, and the costly manufacturing run. In general, in the industry, it's been going through advances at following Moore's law, and as you go down in the process nodes, the cost of the development of a given technology goes higher, and at the same time, because it goes higher, the number of people or companies are able to support and develop these or develop designs on these processes goes down, and then the designers go down. The number of designers goes down. So basically, this is a race to having smaller and smaller number of designers that are capable of innovation and accessing the technology. So in this world, going where we're going, there is a need for a significant number of edge devices that will exist, especially with the so-called Internet of Things. But if you think about it, it's edge devices in general that are smart, that are capable of acquiring data and processing them, and they would need application-specific development, which I call it the right-sized compute and power, things that typically they may not be offered by standard part available in the market. And this is so-called, in the orange here, is the long tail, and it's a variety of products and applications that are suited to different markets. And at the same time, if you think about it, there's a need for a large community of developers to be able to do that. So we do need a multiplication of designers, which is completely opposite to what I mentioned in the last slide, which is the number of designers typically is going down because of the cost of the technology and the limited access. So what we need to do is to simplify the process of making chips and open it to everyone. If you imagine a world to do that, then we can have more designers. So today, or more people having access to design, and they can tinker and develop and innovate and eventually develop new products. So this is the motto that Efabless was founded on, is to make it available to everyone through simplification. How do we do that? So if you think about the app stores in general, let's say Android, so what happened is they simplified and quote unquote democratized, but I call it simplified, the development tools, the business process and framework, and connected to a customer through a marketplace. What happened before then, in order to create a software company or to develop a software and sell it, you would need to structure a company and have funding and have the business development, etc. What happened here by adding the concept of the app stores is that instead of having thousands, now there are millions and millions of people that are developing apps on top of the infrastructure that was available for Android, and that included actually kids. So if you think about it, the software development process was simplified and made available to everyone beyond what it was before the so-called app stores. So if you think about that and apply it to the chip design, again, you would do the similar things, except it's a little bit more complicated, including tools and PDKs and business process and access to customers. Again, we believe that that's how it should be, and that's what the road we're going on. And as my friend Tim Ansel here gave a lot of color, but this is what we're going to, the journey we're embarking on. In the chip world, it's a little bit complex in terms of the number of variables or things that you need to make available, and also the number of parties involved to make it happen. So in order for a person or a company to design a complete useful chip for the market and for an application, whether it's health or agriculture or they need these components on the left here. They need to know what the market is. They need knowledge more than what they know. They need IP and blocks, and they need tools, PDKs, and affordable manufacturing. Any one of them that does not satisfy, it would not produce a useful chip for the market. So there are partial solutions and systems that existed where they provide some of these parts, but at the end of the day, they seem to be meeting the graveyard of not being good enough to be in the market, but they're developed enough to just sit there without use, but they're very valuable designs. So in order to do that, we had to address all these pieces together, and every one of them has a little line item. I'm not planning to, the intent here is not to read that. So I want to jump and say, so how do we simplify the design? Number one, give the technology to make it available and open source, and that's what through the initiative that happened with our partners Google and Skywater. Skywater 130 PDK was made available to the community. That made it's virtually available, very limited. The information of the processes availability is virtually limitless anywhere. The number of downloads per week is about 700 since for the last maybe 18 months, which is, it shows how much propagation or penetration that PDK would have gone or goes. Enables massive collaboration where there's no restriction of exchanging information or asking questions. And then this is, as I mentioned, this is for the Skywater 130 nanometer PDK. Typically, people say, what do I do with the 130 nanometer process? First, I'll borrow the example that Tim Ansel brought. You can do a lot more interesting things by iterating and tinkering and improving in a process that I don't want to call it old. I call it suitable and a good fit for the need that is being able to iterate with different new architectures. I'm showing this picture to show that Intel chips, like something like the Xeon processor, it was made through a 180 nanometer process, and it was a 1.7 gigahertz. Yes, it was a custom processor, but yes, here's a process that people do with here's what people can do with a 130 nanometer. Also, this is a recent data point showing the distribution of designs coming from Europractice, showing that about 50% of the pie here is between 0.8 micron all the way to 90 nanometer. So there is a lot of use in this area, and the diversity of devices and capabilities in these technologies are very special, especially for applications like analog and high resolution requirements. So if you want to see more of these projects, please go ahead to efabless.com/projects. You will get a glimpse of what has been done with this process through the community at large. I mentioned the PDK was downloaded. It actually, literally, I call it went viral because maybe this is a comparison of years of development for specific open source software, and here's within a month or two the number of stars related on GitHub for the PDK. So we also developed through the collaboration, the community has developed and evolved to right now above 3,000 community members only around the Skywater PDK. So imagine the world when you have more, and I would encourage you to go sign up on this link here. The second thing to do to simplify the chip design is to abstract and codify the knowledge. And if you think about converting code RTL into a GDS as a compiler, then while trading off area or performance, but with the condition that it completes, it actually works like a GNU compiler. I have code, I compile it, I have an executable that I can run. And this means that if I don't have to know how the compiler works to produce a binary. So if you think about the RTL to GDS approach in this way, you can present it to the software development community as a compiler, and that actually multiplies the number of potential designers at least 1,000x in terms of capabilities. I don't need to know how the flow works, but I know how to describe my design very well, and I get a physical design that I can use. Also, the tools that are available around the community now are built. They support analog and digital, and there are multiple initiatives that are coming around the world, like Coriolis and Silicon Compiler, and Efabless's Open Lane with the deep collaboration with the Open Road team. So that includes also analog coverage with the analog support. So why does it matter to have open source tools? Again, the limitless availability that enables spontaneous idea realization. Just if anyone can actually get in, try something, and at least simulate it or prove it's going to work in a certain way before even silicon or before even you go to fabrication. And it opens the collaboration with the community both in the design and also to improve the tools as you go forward. Number 3, for simplification, would be instead of making every chip from scratch, why don't we create a base platform that is ready and is resourceful, and you allow the designer to focus on a piece of the design rather than building a whole chip from scratch, which reduces the amount of knowledge required to design the chip. And not only that, deliver them a board. So when you deliver a board, it becomes something that you can plug into the USB and run and treat it the same way you treat an Arduino or a Raspberry Pi. But this is one big component of simplification. So that means I don't need the knowledge actually to go design the pad ring, for example. So, and this is a description of the chip Caravelle that's available in the Sky 130. And then, as I mentioned, you get, if you deliver to the designer parts as well as boards that they can use directly, and get the satisfaction of actually connecting it and confirming their design, that is a big simplification factor. And this is the whole cycle, how it looks like. You design, you put it in a user project, and then the integration of that goes to manufacturing, and then you receive the boards. You can start either looking around by following these links if you're starting an analog or digital design. Number 4 for simplification is to actually build IP blocks or functions that make them clearly identified like Lego. You can put them together without making mistakes. If they don't fit together, they don't fit together. So you can actually have rules around it that are easily checkable, and it would be blocks that can be integrated together, whether it's analog or digital, and have that. If by building that framework, you make it easier. Examples of this blocks, again, you can go to efabless.com/projects, and you'll see examples, and you can see the variance of complexity between the projects. We also have a roadmap that we started with when we started this project with Google and Skywater, and we actually hit a lot of the components here, and we want to do more. We want to collaborate with more people and add more RISC-V cores, or as mentioned earlier, analog blocks or analog tools to generate analog blocks, and then enrich this and in a collaborative way with the community to produce useful outcome for everybody, either for learning or for market relevant applications. As probably Tim Ansel has mentioned, there is a second foundry that is followed based on the involvement or the engagement that they saw and the number of designers that got involved. So you'll see it probably in a month or two. The big simplification factor is related to the cost, because if you want to iterate in the software, is different from iterating in the chip world. So this is where the Google program was, enabled the ability to design something, test it, learn from it, and repeat. So this is a big contribution where Google drove this cool program that allows, it offers free runs, basically you can call it free silicon by Google, that exercises this simplified process to generate designs and allow the community to learn and actually tinker with the concepts. And the condition here is that everything that's being designed to be under an open source license, which allows reuse and also reproduction of the work. So if everyone thinks that their work is easily reproducible by somebody else, and that someone else can actually either modify it or critique it and find an issue, then that leads to a progress in the process. And there is no limitation on who does it, and either all the levels of skills and backgrounds are welcome to participate. And there are examples for, including MPW1. It was great examples of designs, and it was quickly filled with different projects. And there were companies and individuals involved in submitting to this project. One of the key components is, as maybe Tim Ansel mentioned, is that about 60% of the designers on MPW1 were new to the chip design, and that means that the simplification process was actually working. It was followed by MPW2, and again, I'm not going to go through the designs one by one, but that was again a reproduction of how the process works and how the engagement. You can find RAM test chips, embedded FPGAs, and then you'll see our colleague Matt Venn presenting about his initiative in some of the projects here. You can see it on MPW2. So there are many efforts coming from different companies and initiatives that contributed to inside this project in the designs. And here's some quick statistics about the number of designs that are submitted. And there was a noticeable increase in 2020. The first shuttle in 2020 was MPW5, and is 77 submission, and the slots were 40. Now, the community at work, you can see interesting things done. So this is a community member and popular Andrew Zonenberg. We shipped him that RAM test chips, and he created a characterization bench for it, and including temperature characterization. This is another project that was done with this approach, but it's in the context of something else. It was a switching regulator, a student at Stanford University. And then you'll see our friend Matt Venn with different videos and explanations of what he does in an excellent way. You'll see different things. I'll leave them in the slides, including celebrations, as you see. And I'll leave Matt then to cover that in his talk. One of the things that we're limited in general is to, what if I don't want to open source my design, and I would like to guarantee my slot on a shuttle, and I would like to control the time. So Efabless created Chip Ignite, which is exactly the same offering that Google is funding, with the exception that you can choose your own license for commercial application or otherwise. And we created additional options where you can also have the option of getting a complete frame that gives you more area and flexibility to add your own designs. One of the things that happened last year was a program by the IEEE. It was a competition that was it was a very popular, and then it actually to the level that the work was published in different in their magazine over 2 issues. And then also the second year in a row, this is actually the IEEE is running another competition with these types of projects. You can see how these designs are getting to be more complex and available, all open source. So you can see where the movement is going. Chip Ignite in general is similar, as I said, it's similar to the Google offering. You can choose the licensing, and you don't get silicon area, you get a house with electricity and plumbing, and you bring your own appliances. And I leave the pricing here just as an indicator of how valuable the offering is with the complete package, including the tools as well as delivering boards. And if you want to get started, I'll leave some of the links here, and that will be the end of my presentation.